Today we're going to be looking at another one of Plainly Difficult's videos, specifically inside Germany's Chernobyl, if you even want to call it that. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. And I claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
It is June 1989, and the decision to shut down a nuclear reactor has been made. Fear in its country was pushing for a complete abandonment of its nuclear program.
Which would eventually happen, but not in 1989. Sad.
On the wider landscape, reactor shutdowns are not a good thing. In our subject today, it would be hard to argue to keep it open. It had only been running for a few short years, but racked up tens of incidents. Like many problematic reactors, it is of an experimental design, and a design which you probably haven't heard of. It uses radioactive pebbles for fuel. Don't worry,
Oh, pebble bed reactors, those are interesting. Those are often marketed as Meltdown-Proof, just like the Titanic was unsinkable. More on that later.
Dive into this deeper a bit later on in the video.
Oh, just like you said.
The country I'm talking about is Germany, and the reactor is the ill-fated THTR-300. Welcome to Plainly Difficult. My name is John. So sit back, relax, and enjoy the glowing information in this video.
I see what you did there. That's pretty good. Just looks like a ball pit. That's fascinating. This song.
This is the German Chernobyl I alluded to in my RA2 disaster video. Even on the script, I've put Chernobyl in quote marks, as it isn't really. However,
no,
it is in a
the level of this event was nowhere close.
Strange way linked to the RBMK entering grenade mode. As the reactor in today's video experienced a whoopsie just a short period after the old bugger up in the then USSR.
Okay, now this I can see why there's a lot of why they're calling it the Chernobyl, because it was shortly after Chernobyl. Kind of unfortunate timing. Like the 3 Mile Island accident, which was contained, happened a couple weeks after the China Syndrome movie came out. So it's all in the timing, PR management. It's its own separate strategy. Not directly related to emergency response, but it can ultimately lead to unsafe activities taking place. Poor PR management, that is.
With a nuclear disaster under its belt, Germany would completely rethink its power generation methods. Arguably for the worst, as it would rely much heavier on fossil fuels.
Specifically fossil fuels brought in from Russia.
From the, well, east end of Europe.
Yeah.
Saying it like that kind of makes it sound like Russia is the Cockney of Europe.
Never heard anyone say that before, but alright.
An experimental reactor fuel. During the history of nuclear reactors, various different designs have popped up.
Oh yes, Chicago Pile 1 here, or what Minecraft looked like in 1942. First artificial nuclear reactor used during the Manhattan Project. As you can see, just graphite moderators. Only had half a watt, so the graphite's good enough as far as radiation shielding, and you don't need any coolant because it's less than a light bulb.
And for today's subject, an experimental reactor is our main character. It is the THTR type, or thorium helium-cooled high-temperature reactor. The important part here.
Another instance of thorium designs in the experimental phase. The experiments didn't work out well and kind of forgotten about. Which is a shame because there's a lot of potential with thorium.
Here is the word thorium. You see, nuclear reactors most commonly are fueled by uranium-235, which only makes up barely 1% of all naturally occurring uranium.
It's actually significantly less than that.
It's perfect for reactors because it can sustain a nuclear chain reaction. But its rarity is also its downfall, in the sense that it's very expensive to mine and difficult to get your hands on. As such, scientists sought out to find a much easier to attain fuel type for nuclear.
That's actually one of the reasons why it was more widely used than thorium because it's actually not that expensive to get because essentially you have your final product, whereas thorium is more of a precursor since you're ultimately fissioning uranium-233 rather than thorium-232. But thorium-232 absorbs a neutron, undergoes a couple of beta decays, and then becomes uranium-233. And that's what's actually fission. So when people say thorium, it's more thorium goes in, it gets activated, and then becomes uranium-233 when you actually start the fissioning. So one of the things is, you're starting with brand new fuel, you're going to need something like plutonium, which is more reactive than uranium-235 in order to get your reactor going before you have enough thorium-232 converted to uranium-233.
Nuclear reactors. Wouldn't it be grand if you could take something much more common and make it a fissile material? This is where thorium comes into play. You see, if you give the fertile thorium-235 an extra proton, you create thorium-233, which decays into protactinium-233 through beta decay. Then and finally uranium-233.
Yep. That's the summary of what happens.
Which is a fissile material. So, in a thorium reactor, uranium-235 undergoes a chain reaction which releases neutrons, which is absorbed by the fertile thorium-232, which then creates your uranium-233.
You can also, so you start off uranium-235, you could also use plutonium-239, it's more energetic, but the point is something that's fissile.
This allows less uranium-235 to be used, thus in theory making fuel a reactor easier and cheaper, as well as needing fewer startup materials.
That kind of depends where you are and what the economic conditions are. It could be comparable.
Apparently, less nuclear waste, and on top of that, mining of thorium is much easier and safer. But
as far as safer, that's more of a function of the individual reactor design. I would say both, in most modern cases, both reactor designs can be safe, are often safe, at least compared to other forms of generating electricity. So I think you're good either way.
The thorium reactor does have a few drawbacks. The big one is cost. That is, they are far more expensive to construct, maintain and test. Even the fuel is more complex as it needs two types of material. The thorium and the uranium.
Yeah, you need to have your starter fuel.
So that's my idiots.
You could also have a more mixed profile that's a bit more balanced, that you have more uranium-235 that kind of stays in throughout for the duration of the cycle longer, but it's all up to reactor type and individual core type.
Who also had a sound engineering degree. Short explanation of...
Really? That was not bad for someone who's a layperson.
Of the theory of thorium fuel. I recommend a deeper dive going in with someone with a bigger science background. But at the end of the day,
I got you covered.
It's all done just to boil water, to generate steam, to run a turbine, to create electricity. Wow, we're nearly 700 words into the video. I think it's time to talk about the actual THTR in particular, the THTR-300. To say the THTR-300 was experimental because it used thorium is only half of the story. It had one other interesting feature. Do you know how most nuclear reactors have fuel rods? Well, the THTR-300 didn't have that at all. Instead, it used things called pebbles. They're kind of exactly how
these are interesting.
You think, but instead of the things that wash up on the shore, they were balls made of thorium and uranium. Interesting side note that this is actually a video that does contain a lot of balls in it. The concept is actually a video that does contain a lot of balls in it.
You need to have a lot of balls, and you got to keep them close together for an extended period of time to start a reaction.
The concept for the pebble bed reactor has been a long-running one, dating back to the 1940s. However, the first proper crack at it came in the 1960s with the AVR reactor. I'm not going to attempt to pronounce it in German because just look at it. Anywho's,
there you go.
A bigger, more full-scale reactor was envisioned, which was to be the THTR-300. The balls used within this reactor were 6 centimeters in diameter and were made up of graphite with particles of uranium-235 and thorium-232 embedded in it.
And again, the graphite acts as a neutron moderator to slow down the neutrons so they'll cause fission. and with the uranium-235 or 233, depending on the individual ball.
Graphite acted as a moderator, and during operation, approximately 670,000 balls are working through the system.
That's a lot of balls.
Included in this number were some absorption balls made out of a similar material to the control rods. It did also have control rods as well for, well, controlling the reactor's power level.
In this reactor design, you use both balls and rods to control a reaction. It's a little different.
The reactor core was inside a concrete pressure vessel. The theory of operation is as follows. The balls are continuously fed into the reactor core by a feed system. They enter at the top of the core and leave the core at the bottom. The two parts are called the addition device and the pellet extractor. After exiting the reactor, a computer system determines the condition of the fuel ball. If damaged, it is sent to a damaged fuel containment area. If it is burnt up and no longer useful, they are sent to the ball removal device, where the fuel...
Now that's a cool advantage. So you're essentially doing this sort of thing online is pretty cool, because usually, like with fuel rods in a regular nuclear power plant, you have to shut down the reactor, cool it down, depressurize, and then remove the fuel rod bundles with submarine cranes. Whereas these are a lot more small and manageable. You can do this sort of stuff online, which is good.
Is sent off for reprocessing and disposal. I'll come back to how balls are added to the system in a few moments, but I should really mention another part of the reactor design, that is, of its cooling. Now, the reactor uses helium, a gas that doesn't react to uranium, as its coolant. It is pushed around the core using fans at a pressure of 39 bar.
So helium was picked because it's a noble gas, so it doesn't react with anything chemically. And it has decent thermal conductivity, at least for a gas. Obviously, something like water is better, but if you're using a gas-cooled reactor, not unheard of. But that's also the reason why you have to have the graphite moderator, because helium doesn't slow down neutrons well. So you have a separate object as your moderator than as your coolant. Contrast that to a pressurized water reactor where the water both slows down your neutrons as well as cools the core.
Uses the Rankine cycle to heat up water in an exchanger, which then turns into steam to turn the turbines and then create electricity, and that's all pretty standard stuff.
Yeah, the Rankine cycle is the same steam production cycle that's existed for the past couple of hundred years that's been used in every power plant from coal to natural gas to nuclear.
However, due to the coolant being gas, the reactor pressure vessel and auxiliary parts needed to be gas tight. As such, when adding fuel balls to the system, escape of the high pressure, very hot and radioactive gases has to be avoided. The additional device has two control valves that work like an airlock.
That's
type
fun.
that you get on same
You're showing
spaceship.
the concept.
The ball was added and the inlet valve was close behind it. The chamber is then pressurized, and after the required pressure is met, the outlet valve is opened, allowing the balls to enter into the refueling system. After the outlet valve is closed, the lock is relieved in two steps. In the first step, to a pressure of 1.1 bar in the container, and the second step into the exhaust air chimney. The addition device is normally operated automatically. However, it can be operated manually when required, for example when adding less than the 60 balls allowed in the software programming. Now,
most methods of reactivity management, whether it's control rod movement, raising or lowering turbine load, or in this case, adding or removing balls, generally routinely performed manually with a reactor operator, peer checker, and supervisory oversight, because after all, you're manipulating the reactor directly and it's under the highest level of scrutiny. At least that's the way it is in the US now. I can't necessarily speak to Germany in 1989, but in this case, you would at a minimum need a peer checker when manipulating your balls.
Now the THTR generated, you guessed it, 300 megawatts of electricity. Construction took place between...
That's pretty small compared to a commercial operating nuclear reactor, which are usually at least 1,000 megawatts, but like you said, experimental, so this is an experimental reactor, so you're not going to make a full-sized one.
1970 and 1983, achieving criticality in the same year. It would not generate electricity until 1985, and the highly complex reactor would prove to be rather problematic, which leads us on to the disaster. the disaster. It is the evening of the 4th of May 1986, and an operator at the THTR 300 is preparing to manually load the reactor system. They were requested by the plant physicist to add 40 absorber balls. Now, they opted not to use the automatic system today due to the number of balls. It is optimised for loads of 60.
And that's not uncommon. Yes, the automatic systems typically exist, but if you're doing, say, something that's, especially if something's a little different, you're generally going to want to have some level of manual operation.
Being asked to insert 40 could cause issues. However, running in manual mode opens up its own risks, in that you can make a mistake. The reactor is running.
That's true, though a lot of times, depending on the design of your reactivity control system, there's at least interlocks in place that you can only do so much manually. Now, I don't know the specifics if there's a limit to how many balls you can add or remove manually, so don't know for sure. But if this reactor, say, existed today, there's definitely limits on how far you can move control rods, for instance. And those limits aren't just administratively, those are hard limits with electrical and mechanical interlocks that the system just won't let you do it.
At an output of roughly 40% of its normal maximum output. And all seems good. However, as the operator began the loading process, they made a mistake. The chamber was filled with helium. When the operator opened the automatic outlet valve, the automatic seal monitoring of the valve was activated, and the connection between the valve and the relief vessel opened. This prevented the balls from entering the system. In doing so, radioactive gases were able to escape into the chamber. Noticing that no balls had entered the system, the operator switched to the additional device back into automatic mode. This would prove to be another.
That's bad. A standard malfunction response would be to put your device in manual. Whether it's control rods, if they're malfunctioning, the first step is put them in manual. If you're having issue with, say, a boric acid pump, then it would be to turn off the pump. The point is to effectively stop the transient or stop the malfunctioning component. And then evaluate, and then verify the reactor is stable, or if not, make an adjustment, and then go into troubleshooting whatever the issue is.
Error. As you see, part of the automatic program, the chamber was meant to be vented to atmosphere, which in our case was filled with radioactive gases. The vent opened and aerosols of around 50 becquerels of radioactivity were released.
That's not very much.
It opened and aerosols of around 50 becquerels of radioactivity.
That's not much at all. And considering this is going out into the environment, it's going to be diffused pretty quickly. The main hazard, probably carbon-14 from the graphite. So the graphite becoming activated with neutrons. It's actually mainly used in radiocarbon dating to find out how old something is, which is interesting. But yeah, 50 becquerels. The Environmental Protection Agency standard limit is 148 becquerels per cubic meter. And that's just for at your house. So 50 going out, being diffused into the atmosphere, so not concentrated anywhere close to a cubic meter, then yeah, that's not much.
Were released. Now, this isn't a massive amount. The reactor was allowed to release around 10 becquerels per day, but it would be significant for another reason, which I'll come back to in a little bit.
It's not a lot, but yeah, it's a mess. The reactor operators didn't do what they supposed to. It was an unplanned release above their gaseous effluent limit, so there's going to be some people written up, there's going to be some violations reported, there's going to be some damages assessed, but I wouldn't call it a disaster, at least not the accident itself.
Anyways, the operator realised their mistake and closed the chamber. However, a surge of gases shattered some of the balls destined to enter the system. The system was shut down after this, and roughly from start to finish, the whole event had only lasted 20 or so minutes.
Oh, and the other thing they get is because there were actual cracks, that's considered fuel damage, though probably assessed a little differently because we're talking pebbles rather than fuel rods. But yes, fuel was damaged, but they didn't break the reactor. So this was way less significant than 3 Mile Island, for instance, where they actually had a meltdown in the sense that fuel overheated, melted, though it did not escape their containment building. But here, the amount that was released was not enough to cause harm. Significant in that, again, they violated their limits, and it was a mistake. But no one's getting hurt from this. Now, this sort of reactor design has come to light recently in that people are claiming that they're meltdown-proof, but they're not. Even the more recent one, China's HTR-PM project, it's certainly not immune to damage or failure or safety risks or anything of that case. That's just not a thing that you're completely immune to that or necessarily any more proof than anything else. Now, they are heavily resistant. Those pebble bed reactors can withstand extremely high temperatures, upwards of 1600 degrees Celsius, and the cooling is passive, but you can have extreme conditions such as a loss of coolant, so loss of the helium, or structural blockage from, say, like the building itself gets damaged from like an earthquake or something. Highly unlikely to happen, but losing your cooling profile, even if the system is passive, will cause the reactor to overheat eventually. Not to mention graphite can oxidize and ignite at high temperatures, causing a fire, not unlike the Windscale accident in 1957. Now again, PBRs can be very safe, and for talking specifically about fuel overheating, I would say they're even safer than zirconium alloy-clad fuel rods, specifically because they're more resistant to high temperatures, and zircaloy has the tendency to release hydrogen gas at extreme temperatures, which is explosive. So you're not going to have that to worry about. But graphite has its own flammability challenges. But the point is, nothing is indestructible. And especially considering this is a claim by China, a lot of their safety claims are unverified. And saying something's meltdown-proof, I really don't like it when people do that, because if throughout its operational history, assuming something like this takes off, if later incidents reveal some risks, even if, no meltdowns occur, but just observations throughout its operational history reveal some sort of vulnerability, then it's just going to be a reputation tank. It's just going to tank the reputation. But this is nuclear. It's going to have passive safety, robust safety procedures, monitoring, maintenance schedules, everything you can to make it as safe as possible. But really don't like saying meltdown-proof.
But those 20 minutes would contribute to the changing of a whole country's power generation course, the aftermath. In the immediate aftermath, the reactor was shut down, but would be brought back online after improvements by adding a filtration system to the exhaust chimney and better instructions and procedures on the feeding system. The event was played down initially. An anomalous informant from staff of the THTR reactor informed supervisory authorities and environmental associations about a not reported emission on the 4th of May 1986. The nails were firmly in the coffin for the reactor. You see, the radiation release was pretty minimal, barely exceeding the 180-day emissions limit. Any other time, the event would have probably just been a footnote, and a non-reporting would not have probably been noticed. But a small case of a self-deconstructed
Non-reporting is damning, though.
RBMK reactor you probably haven't heard of in a place called Chernobyl occurred on the 26th of April.
Yep.
Due to this disaster, all across Europe, radiation monitoring was on high alert, as a radioactive cloud drifted over Germany and the rest of Europe. During this time, heightened rates of cesium-137 were found. Amongst other radioactive isotopes,
so cesium-137 is one that's going to stay around for longer after the accident because it has a half-life of about 30 years. It's actually not the most hazardous immediately after. That would be iodine-131, but it's got a short half-life on the order of days. So if you're talking weeks, months, years, you're not going to see it. Good rule of thumb for half-lives is 7 to 10 half-lives elapsed. It's gone. Just depends whether you pick 7 or 10, it depends how conservative your radiation protection program is and what the isotope is.
Was protactinium, or Pa-233, What was interesting was that the PA-233 is a direct indication of a release from a thorium-fueled reactor.
And that's because, I mean, its number is 233. Fission products, which are probably the worst in terms of actual dose, are centered around atomic numbers 95 and 140. Nuclear engineers call this the Dolly Parton curve for highly scientific reasons. But that clearly fingerprints to the intermediate step of thorium-232 turning into uranium-233.
This was not from Chernobyl. Thus, something must have happened at the nearest thorium reactor, the THTR-300.
Yep.
As such, an official investigation was launched into the emission release. It was found that the release wasn't massive. However, with our own micro Chernobyl, right after the real Chernobyl, the problematic experimental reactor had to go. Germany.
Interesting that this is kind of called Germany's Chernobyl because it also includes their response to Chernobyl, which is in the relatively similar time frame.
Had a very long-running anti-nuclear movement. Protests often manifested throughout the years whenever an incident at a nuclear power station had occurred anywhere else in the world. Take, for example, this picture post 3 Mile Island. Just 2 years after the release, the reactor was shut down and deactivated in 1989, not long before reunification of Germany and the further culling of nuclear power stations that came with it from the former East Germany.
So, what did we learn from this? Mechanical challenges, mechanical failures within the ball system. So, there's something to be said about reactivity control and placing things in a safe condition before you do subsequent actions, such as placing the system back in automatic. There's learnings around operational complexity for experimental reactors, especially because it's new technology. You're not entirely sure how it's working. And you often, when doing experiments, put the reactor in conditions, power levels that you sit at that are not 100% hot, steady, normal, because you're doing tests. You're trying to see how this sort of thing works. And there's higher risk associated with those sort of tests than, say, testing at a commercial facility. But the big one is timing is everything, because even a minor nuclear incident can result in massive public backlash. Also, don't try to cover anything up, even if it's minor.
By 2023, all of Germany's nuclear power stations had been shut down.
Sad.
Interestingly, the country in the same year had a consumption of fossil fuel sources that accounted for 77.6% of the country's energy usage.
Where else are they going to get their energy? Solar and wind? No.
Personally, I think it was a little bit short-sighted, but hey,
it was a lot.
Not my place to judge. So that's my video on the THTR-300 reactor. Do you have any more reactor disasters to suggest? Let me know.
That was a good one of the less commonly known ones. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.